Lecture 20, Conserved Quantity, Killing Vector and Geodesic. I would like to emphasize that Killing Vector and Geodesic, they play an important role about conserved quantities. You see, as you see here, a particular case where the inner product it is conserved. You see, you will see here this derivation. Now, conserved quantity associated with the killing vector. You see, that's the first part. Now, a killing vector KV, the killing vector field U, on a remaining manifold satisfies the killing equation. This is the killing equation. This is number 1. You see, this implies that the Lie derivative of the metric vanishes. Okay. Also, I would like to emphasize that this over here, okay, this is symmetric. The skew symmetric because this is the killing equation. So, if you put in the right hand side, this is minus. You see. So, this is a skew symmetric. Okay, the equation leads to a skew symmetric relation. So remember that this equation it came from the Lie derivative of the killing vector of G set to equal 0. Now, on the other hand, recall that geodesic is a curve phi of t on a differentiable manifold M parameterized by this case on the affine parameter t, such that the tangent vector vi are the components, the covariant, this case, covariant components of the tangent vector v, okay, at the curve, acting on the curve. So dxi of dt, remember xi is a coordinate which belongs to a chart. Okay, at a given point P on the manifold. We derive this. So, this is a parallel transport along the curve. This means that the covariant derivative of V of the same vector V is set to equal 0. That's how to obtain the geodesic curve. So, in terms of components, that's a Vk, covariant derivative, okay, Vj is equal to 0. That's a geodesic equation. This is number 2. Now, let's show that the derivative with respect to the parameter t with the inner product uv, which I call c, this is equal to 0, which means that c is a constant. So inner product is a constant. That's what we want to show. You see? So this is conserved along the geodesic. I want to prove this. Now let's start. This operator, you see d of dt, or this blank space, is equal vk, covariant derivative acting on this blank space. This blank space could be a scalar, a vector, and a tensor of any order. See, second or third order tensor. So this is an operator. Let's apply this operator to the scalar function c, which is the inner product uv. Now recall that's the inner product, okay, of uv. This is partial xi, partial xj. They belong to the covariant space, and they are, in this case, this behaves like unit vector, but they are not. You see, from the definition, you see that this relation over here, you see, the inner product of the basis, okay, is Gij by definition. That's a metric, Ui, Uj. So just substitute here by Gij. Now, this the derivative of c respect to t, okay, I develop this over here. This is the same as vk, number k, this uj, vj. UJVJ is the inner product. You see, I just substitute the inner product on this blank space over here, okay, and write down here. Now, let's develop the first term from 1. You see, this is equation 1. This is skew-symmetric. So, you develop this is minus, skew-symmetric. Now, that's important because this over here, okay, I just substitute I and J, K and J, because K is dummy and J is dummy. So I can set here Vj, Vk, I swap J and K. You see, because both are dummy indices. So I can write the blue term, see the blue term over here is equal minus this term. So I can write from there, this leads to the sum of this same term, okay? This is twice the same term, this is equal 0. Then the blue one, you see, that's the blue one, the first term, this will be 0. Now, to show that this CDT is equal 0, now I want to prove that the green one, the term over there, is also 0. So there's a second term, okay? There's a green one. Again, from equation 2, you see, equation 2, you just take a piece of paper and write, you say, and compare on this board. So it's just VKUJ applied to number KVJ. This is equal to the same UJVK, number KVJ. Attention now. You see, look, it's easy to see it. It's easy, okay? That in this case, I will have UJ. You see, UJ. You see that. Forget about UJ. You see, VK. In this case, number KVJ is 0 from equation 2. You just look at here. You see, you just set this equal 0, and then this one that's follow, okay, will be UJ times 0, okay? This 0 comes exactly from relation 2. It's quite easy. Then we'll prove also that the second term, the green one from equation 3 is 0. So now we obtain this important result, that this here dt, this is equal 0. You see, from relation 3. From relation 3 over there, I just substitute the blue in the green one, then I see that this is 0, which implies that C is the inner product is constant, which we can say that the inner product is Gij, Ui, Vj. This is Uj, Vi. Just apply Gij, okay? In this case, or Ui, okay? So it's easy. That's a property of Gij. So C is conserved. So that's our goal, to show that derivative with respect to T, the parameter T of the inner product is 0, which means that the inner product is conserved when you move along the geodesic. See, that's it.